Welcome back to Inorganic Chemistry. In this chapter, we'll discuss simple models for bonding. In part 1, we'll look at Lewis structures, reviewing how to draw them and also how to determine formal charges. In part 2, we'll look at molecular geometry and the polarity of molecules. So to remind you from general chemistry, the octet rule, or octet trend, as we'll see there are exceptions, describes how atoms tend to join to make chemical bonds. And the idea is that chemical reactivity of the noble gases, of the group 8A elements, well, they don't react. They're chemically inert. And that's why they're called noble gases. They're too pure to mix with anyone else. And the reason they don't make bonds is that they have a filled valence level with 8 electrons, except for helium, which is a filled valence shell with only 2 electrons. So then that means there's no electrons available to make bonds. And so other elements will change their electron configuration, their valence electron configuration, to be more like that of the noble gases. In other words, 8 valence electrons is a stable condition, and so elements will react to form octets. So octet is Latin for 8. So the rule of 8 valence electrons is a stable configuration. So elements will react to form octets. They react in 2 different ways. They can react by sharing electrons or transferring electrons. So when they share electrons, that's what we call a covalent bond. Meaning to share their valencies. And this occurs between 2 atoms of nonmetallic elements. And then the ionic bonding is when atoms will transfer an electron in order to also match the octet rule. So we're going to use this octet rule, count electrons as they're shared to see if atoms are completing their octets in a chemical molecule, which is the basis of Lewis structure. So to remind you, molecules are clusters of atoms held together by covalent bonds. Other chemical compounds, ionically bonded compounds, are not considered molecules. Some of the pure elements have molecular forms, hydrogen, nitrogen, oxygen, etc. You can see in their pure form, in their normal state, they exist as discrete molecules rather than atoms or solids. And later in the semester, when we review the main group element chemistry, we will see the molecules of sulfur, for example, that exist in solid sulfur crystals. And then there's also molecules made up of more than one type of atom, and more than 2 atoms would be called a polyatomic molecule, and water is an example of that, and the most famous chemical formula, H2O. So let's just review how we can understand the bonding of water using the Lewis dot model, Lewis dot representation. So this is the molecular formula for water, and the first step is to sum all of the valence electrons from the elements in the compound. So there's 2 hydrogen atoms in the molecule. Each one has one outer electron, so that gives us 2 outer electrons from the hydrogen. The one oxygen atom has 6 valence electrons, so there's one of those that contributes 6. So the total we have to work with are 8 outer electrons, or 8 valence electrons in the molecule. So here's our molecular formula. Here's our 8 valence electrons. And then we need to arrange the atoms in bonding order. And this is determined empirically. Usually the rule is that the most metallic nonmetal will go in the center. Hydrogen always goes on the outside. So here in water we know oxygen is in the center. And now we'll take our valence electron pool and start to fill in to make the bonds. So we did that here. We took 2 electrons, put them between the hydrogen and oxygen to bond the atoms together in a single covalent bond, and put these 2 in the other oxygen-hydrogen bond. And that leaves 4 electrons from our 8. And so those will fill around the central atom in order to complete the octet of oxygen. So we have lone pairs and bonding pairs of electrons. Now let's count and see that we have indeed fulfilled the octet rule. So we count the electrons around the oxygen. 1, 2, 3, 4, 5, 6, 7, 8. So oxygen has 8 electrons. It meets the octet rule. Hydrogen, there's 2 electrons here. Hydrogen, of course, doesn't need 8, only needs 2 electrons to fill its valence shell, and same with this hydrogen. And since these electrons in this bonding pair are being shared in the covalent bond, we can count them as both helping oxygen fulfill its octet and hydrogen fulfill its 2 electron structure, electron configuration. So water is a stable molecule. We can represent water using the molecular formula, empirical formula, H2O. We can represent it using the Lewis structure that we just drew, Lewis dot structure. We can condense the bonding pair as just a line representing that single covalent bond, so that's a line drawing. We can further condense it. We could look at, well, what's happening in 3 dimensions. The molecular geometry of water is bent, as we'll talk about later in this chapter. And so a ball and stick model, we see the oxygen, hydrogen, and that they're connected by the single covalent bond. Or we could use a space filling model, which is more accurate, to show the relative sizes of the atoms filling up 3-dimensional space, but we can't see the bond in that model. Okay, let's do a little more complicated molecule, carbon dioxide. We have 1 carbon atom, which each carbon has 4 valence electrons, so that's 4 toward our molecule. There's 2 oxygen atoms in the molecule, 6 valence electrons each, so that's 12. 4 plus 12 is 16 total valence electrons. Here they are all arranged. Bonding order, carbon's in the center, so we take our pool of valence electrons and add bonding pairs between the carbon and oxygen. That's what's done here. And so we make 1 bonding pair, another bonding pair. We have lots of electrons left over. We don't have octets yet. So the next step usually is to complete the octets of the outer atoms. So you can see we have 1, 2, 3 bonding pairs, or three pairs of electrons that could become lone pairs there. 3 pairs of electrons that could be lone pairs there. But if we look here, we see that oxygen has 8 electrons around it, but carbon only has 4 electrons around it. So carbon does not have a complete octet. So to do that, we need to move a lone pair from oxygen right here between the carbon and oxygen to make another bonding pair, which is covalently shared with the carbon, and so these 2 still are going to count toward the oxygen octet. So that's what we've done here on both sides. And so We have lone pairs like we had before, and now we have bonding pairs. But now we see we have two bonding pairs between the carbon and oxygen. So that's called a double bond or double covalent bond, and that will fulfill the octet rule. We can count here around the carbon. We have 1, 2, 3, 4, 5, 6, 7, 8 electrons, and then around the oxygen 1, 2, 3, 4, 5, 6, 7, 8 around the oxygen as well on both sides. So this Lewis dot structure for carbon dioxide shows it's a stable molecule as drawn with two carbon-oxygen double bonds. Now, another way to evaluate the stability or viability of a Lewis dot structure is to use the concept of formal charge. And in formal charge, this is not the actual charge like ionic charge. It's a way of counting the electrons. And the formula is that we take the number of valence electrons of the atom we're looking at from the periodic table, and then subtract from that value the number of lone pairs around that atom in the molecule, and then also subtract half of the bonding electrons. So this assumes equal sharing of the bonding electrons. And then the formal charge, the sum of the formal charges in a molecule should equal the total molecular charge, like if you had a polyatomic ion. So let's do this for oxygen, for example. So oxygen here, we look at the periodic table, oxygen has 6 valence electrons, and in the water molecule it has 2 lone pairs, or 4 lone pair electrons, and then it has 1, 2, 3, 4 bonding pairs, but we're only going to subtract half of those 4 bonding pairs. So that means 6 minus 4 minus 2 is 0. So formal charge on the oxygen and water is 0. Let's look at the hydrogen. Hydrogen has a 1 electron valence from the periodic table. There are no lone pairs, and there is 1 bonding pair, so half of 2 bonding electrons. So 1 minus 1 equals 0. So the formal charge on each hydrogen is 0. 0 plus 0, the total charge is 0. So that works for water. For carbon dioxide, we could do a similar calculation. Let's look at the carbon first. So carbon from the periodic table has 4 valence electrons. There are no lone pairs around the carbon, and there are 1, 2, 3, 4, 5, 6, 7, 8 bonding electrons. So 4 minus half of 8 is 0. Oxygen here, again, oxygen has 6 valence electrons. There are 4 lone pairs and 1, 2, 3, 4 bonding pairs. And so this formal charge on oxygen and carbon dioxide is also 0. Well, this means these are good Lewis structures, because the best Lewis structure would be one that has less formal charges. Yeah, let's add that rule here. We want to minimize formal charges. So we don't want lots of formal charges around the molecule. So, and another way to determine the validity of Lewis structure is to put the formal charge on the right atom. So if we have a negative formal charge, that should be on the most electronegative atom in the molecule. Conversely, the positive formal charge should be on the least electronegative atom. And we'll talk about electronegativity in the second part of this chapter. So Lewis structures are very useful for understanding the bonding of molecules, but there are exceptions and limitations. There's exceptions to the octet rule, as we'll see in class. And there are additions to tweak the Lewis structure, concepts like resonance. And then we also have molecules like water, where, like dioxygen, where according to Lewis structure, we should have this structure for dioxygen, or an oxygen double bond in the molecular element dioxygen. And this fills its octet, this fills its octet. That looks right. But experimentally, oxygen is paramagnetic, and we'll talk later what paramagnetism means, but for now that means oxygen is going to be attracted to a magnetic field, and that indicates the presence of unpaired electrons, or net electron spin. So where are the unpaired electrons? Well, if we draw the Lewis structure this way, we would get unpaired electron on each oxygen atom. But that doesn't, 1, 2, 3, 4, 5, 6, 7, that doesn't meet the octet rule. That would not be a good Lewis structure, but that actually fits the experimental results better. And so what we need is, as always in science, a better theory to fit the experimental data. This unfortunately is going to be a more complex theory, which we're going to talk about in a later chapter called molecular orbital theory. So thank you for your attention, and next time we will talk about molecular geometry and electronegativity.